Another concept that we need to think about is effect size. We've already looked at some aspects of effect size through correlation. So the Spearman's and Pearson's correlations are examples of effects. Where you have a small correlation, then it's 0.1, that's a small effect size. If the correlation is 0.3, then it's a medium effect size. If it's greater than 0.5, it's a large effect size. The maximum is 1, where the two things are completely deterministic of each other. Now you'll notice that a large effect size of 0.5, that has a coefficient of determination of 0.5 squared, which is 0.25. So that's only explaining 25% of the experimental variation, but from the x-coordinate. So even though that is a large effect, it's still not completely explanatory. So that works when you're looking at two different variables and the relationship between them. But what happens if you've got two groups, you've got treated and untreated? How do you calculate the effect size? In which case it's a treatment effect between those two groups. So to do that, you use what's called Cohen's d. So Cohen's d is the sample mean of the first sample, which is represented by x bar, minus the sample mean of the second sample, divided by the standard deviation. So this is telling you how many standard deviations there are between the two means. And that's important to think about. Now, what kind of values does this take? So a d of 0.001, that's a very small difference between the two means. A small difference is 0.2, medium's 0.5, so it's still only half a standard deviation between the two means. Large is 0.8, very large is 1.2, and a huge effect would be 2. Now this is very similar to the 1.96 or 2 standard deviations either side, where you get into the tails of the distribution. This is telling you that the means are very different from one another, and it's not conceivably possible that they could come from the same hypothetical mean. Now, why does effect size matter? Well, it matters because it tells you how large your sample needs to be before you can see that there's a difference between the two means. Now, every time you do an experiment, it's going to have its own effect size because the sample means are different and the standard deviations are different. So what you're looking for is that the sample is large enough so that the standard error of the mean of that sample is less than the difference between the two means. It's less than the treatment effect size. So the standard error is described as the standard deviation of your sample divided by the square root of n. As you make n larger and larger and larger, this becomes a very small number. Technically, if you go to infinity, it becomes 0. So you could have two means, one which is 10.1 and the other which is 10.11, and you can distinguish them if you have a big enough sample size, because you can get arbitrarily close. And this is a product of what's called the law of large numbers. So as our sample size gets bigger, we can tell the difference between treated and untreated to a very high degree. Arbitrary small differences. So sample size needs to be calculated when you know what your effect size is going to be.